Okay, hi. So in this video, we're going to start talking about the Galois group of a cubic equation, of the splitting field of a cubic equation. So let me start here by, okay, so let's say F, the field, and F is a cubic polynomial, degree 3 polynomial. Let's say, let K be a splitting field of F over F. Now our goal is to characterize the Galois group. Find the Galois group of K over F. Now, first thing you can know is that this polynomial here, you can assume that it's irreducible. Because if it's not irreducible, then you'll be back to a situation that you already know how to deal with it. Right? If the degree is 3, if it's not irreducible, then it factors either into all degree 1s, in which case the splitting field is just F itself, or into a degree 2 irreducible and a degree 1, and now you're back to the situation of Galois group of a quadratic polynomial. So let's assume F is irreducible. Okay, so now let's start with an example here. A simple example. And actually, the case that we're going to be most interested in anyways. So let's start with taking F to be Q. F to be Q. Let's take a polynomial, say f of x is a cubic and irreducible. How about x squared plus, x cubed plus x plus 1 plus x squared plus 1. Okay, now, well, this is polynomial degree 3, coefficients in Q. Well, being irreducible is the same as having no roots in Q. And well, okay, so now roots are in Q. Okay, so this is because this guy has integer coefficients. The roots of it, if they are of the form A over B, if A over B is a root, A and B integers, that would imply that A divides the constant term and B divides the coefficient of x cubed. A divides 1, displaying A and B relatively prime. So this is, I think, this is what you've seen this result, right? This is, I think, maybe exercise 61 or 60 something from Rotterdam. So okay, so because of that, we only have to check 1 and 1 to see here, to see if this guy has a root in Q or not. Well, 1 is clearly not a root, and so and same with minus 1, right? Minus 1 plus 1 is 0, and then you're left with a 1. So no rational roots, so it is actually irreducible over Q. Okay, so what's the Galois group of F over Q? Okay, so K is the splitting field. And we may assume that because for any two splitting fields, there's going to be an isomorphism between the two splitting fields which fixes Q in this case. So you may pick one splitting field and calculate your Galois group there. So let's take the splitting field of F over Q in C. Take the splitting field in the complex numbers. Now, the the number of elements of the Galois group. So on the one hand, so the number of elements of the Galois group of K over Q, K being the splitting field, this number of Galois group is equal to the degree of K over Q. Why? Why? Okay, so exactly, because K is the splitting field of the polynomial, so that's good, that's important in this result. There's another thing that is important, which is that so the general result, when you want to apply theorem 51, you also need to make sure that the irreducible factors of this polynomial are separable, that the irreducible factors of this polynomial don't have any repeated roots. However, because you're working over characteristic 0, that condition is always guaranteed. Remember, in characteristic 0, any irreducible polynomial is separable. It doesn't have any repeated roots. So you don't have to worry about that condition. Just the fact that K is a splitting field tells you that the Galois group of K over Q, its number of elements is the same as the degree of the extension K over Q. Okay, so this is one result to keep in mind. Another result to keep in mind is the following, that this is what we did in the last video, that you can think of the Galois group of K over Q naturally as a subgroup of, let me make sure we don't lose the camera, you can think of the Galois group of K over Q naturally as a subgroup of the group of the symmetric group, the group of all permutations, on the set of roots of F in K. So in this case, okay, so how many roots does F have? This is, well, F is degree 3. If it's degree 3, there's going to be 3 roots. This is isomorphic to S3. So the Galois group is a subgroup of that. So now, what do we get here? So the number of elements of the Galois group divides the number of elements of S3 which is that degree. This divides the number of elements of S3, which is 6. Now, here's our